Welcome to this introduction to passive intermodulation, PIM. I am Dag Strandeby, working at Orebro University and doing research on PIM together with EMC specialists at Nolato in Hallsberg, Sweden. The contents of this presentation is crowded bandwidth, what is PIM, nonlinearity and MIM diodes, and finally some words on measurements and goals. There are many services using wireless technologies today. This frequency chart, ranging from 30 MHz to 300 GHz, shows frequency allocations for different services. As can be seen, it's quite crowded. In this presentation, we will focus on the range 700 MHz to 2 GHz, where for instance common GSM and UMTS services can be found. As an example, take the primary band, PGSM 900. Since we're dealing with a full duplex system, it has an uplink band 890 to 915 MHz and a downlink band 935 to 960 MHz. Each band harbors 124 channels. Uplink is from the handset to the base station and downlink the reverse. Assume a user is allocated 914 MHz uplink frequency. Then it follows that 959 MHz will be the downlink frequency. The duplex distance is 45 MHz. Now let us look closer to what is going on in the base station when a single user is present. First we will find a powerful radio transmitter for the downlink at 959 MHz. There is also a sensitive radio receiver handling the uplink at 914 MHz. The two units are connected to a duplex filter to be able to share common antenna cable and a common antenna. The duplex filter ensures that the incoming and outgoing signals are routed to the right units. The filter also maintains correct impedance matching. Finally, the signals travel to and from the user wirelessly. Transmission capacity and the quality of a given link depends on the signal to interference ratio. That is the power S of the desired signal divided by the power I of interfering signals at the same frequency. It is imperative to minimize interference to maximize the capacity and hence the revenue of the base station. Too strong interference can block a sensitive receiver completely and make the channel unusable. Let us go back to our base station example before. Now we would like to introduce a second user into the system, so the present user will be noted user 1, and the new user will be number 2. As can be seen in the figure, we have added a new transmitter and a new receiver. The frequencies for user 2 are 891.5 and 936.5 MHz respectively. Note that since we're using different frequencies, the users can coexist without interfering each other. This is a typical frequency division multiple access, FDMA scheme. The antenna and cables now handle 4 signals simultaneously. Everything works just fine, but pretty soon trouble is on its way. Now let us address the question, what is PIM? PIM is an acronym for passive intermodulation. Let us start with passive. Passive in this context means we're dealing with parts that do not have a power supply. It can be a cable, a connector, or a cable joint. It can even be a non-electric mechanical part, for instance a bolt or a cable clamp. Intermodulation means that two signals with frequency F1 and F2 respectively may under unfortunate conditions produce a new signal with frequency F3. For example, F3 may be obtained by taking 2 times F1 minus F2. Assume we have an issue in the cable joint in our base station. Unfortunately, the faulty part generates a new signal with frequency F3, which equals 2 times F1 minus F2. The two strong signals in the downlinks have frequencies 936.5 and 959 MHz. Unfortunately, these two signals will produce a new signal with frequency 914 MHz, which happens to be the same frequency as the uplink of user 1. There is reason to believe that the new signal will interfere severely and the uplink of user 1 will be blocked, meaning that the link is dropped. In this figure, an alternative scenario is shown. The problem is not located in the equipment itself, but rather in an external part picking up the electromagnetic fields from the antenna. From the two strong downlink signals 936.5 and 959 MHz, a new signal is created 940 MHz, which is radiated back into the antenna. The result is the same as before, receiver 1 is being blocked. In this case, the external part may be a rusty bolt or another purely mechanical device. The third item deals with nonlinearity and MIM diodes. These are the mechanisms behind PIM and create signals with new frequencies. In cables and connectors, quite strong radio frequency currents will flow due to the radio frequency voltage being supplied from the transmitters. Further, metallic objects in the vicinity of the transmitting antenna, for example a bolt, may pick up the electromagnetic field from the antenna. This will cause a radio frequency current to flow in the part, which will in turn generate the voltage and retransmit the signal with a new frequency. The diagram shown is a current versus voltage plot, where the voltage over the device is on the x-axis and the resulting current through the device is the y-axis. In this case, the function is a straight line passing through the origin. This is a typically linear behavior. The current is simply proportional to the voltage, and the slope of the line corresponds to the electrical conductance. As we saw on the previous slide, a linear function can be expressed as the current I equals multiplying the voltage V by a constant K. Now assume that the voltage is comprising of two cosine signals having frequencies F1 and F2. The resulting current only contains the original frequency components F1 and F2. No new frequencies are created. This is the ideal situation. If the voltage current function is not a straight line, but curved in any way, the function is said to be nonlinear. It is obvious that there is an infinite amount of nonlinear functions. Assume that the current I is equal to the voltage raised to 3. We apply the same voltage with frequency components F1 and F2 as earlier. After expanding the parenthesis, the current will contain 4 terms. Using standard trigonometric formulas, the 4 terms can be rewritten. Now we can see that there is a number of new frequency components present. First of all, we find the frequency components F1 and F2, the original and desired ones. We also obtain some new frequency components, 2 times F1 plus F2, 2 times F2 plus F1, 3 times F1, and 3 times F2. All these signal components have frequencies that are considerably higher than F1 and F2 and can hence be filtered out. In most cases, these signal components do not cause any problems. The problematic frequency components are 2 times F1 minus F2 and 2 times F2 minus F1, since they are close to the desired frequencies F1 and F2 and cannot be removed using filters. This is a simplified example. In reality, there are many more frequency components to take into account. Often, the new signal components may not be experienced as discrete frequencies, but rather as a general increase in the noise floor. A new example, the current function is a combination of a linear term, the voltage V, and a nonlinear term, the voltage V raised to 3. C is a constant that expresses the amount of nonlinearity in the function. If C is 0, the function is purely linear. Now, the interesting thing is to find the ratio between the amplitude of the interfering signal components and the amplitude of the desired signal. It is also interesting to see how this ratio is affected by C, the amount of nonlinearity. Or put it in another way, how much nonlinearity do we need to get a certain amplitude of the interference? First, the amplitude D of the desired frequency components F1 and F2 are given by 1 plus 3 times the constant C divided by 4. The amplitude U of the interfering signals are given by 3 times C divided by 4. The ratio between the amplitude of the interfering signals and the desired signal components can be found. The ratio can also be expressed in decibels relative carrier. The implication of this is that for PIM in the range -140 to -160 dBc, quite minute nonlinearities are involved. This diagram shows, in blue, a linear function and some nonlinear functions, corresponding to the figures on the previous slide. As can be seen, for small signal levels, all the curves are basically linear, but for stronger signals, the nonlinear behavior becomes apparent. In the general case, the interfering frequencies can be found by m times f1 minus n times f2, where m and n are integers. The order of the intermodulation products is m plus n. In our previous example, we had m plus n equals 2 plus 1 equals 3. Hence, we had a third-order intermodulation situation. The nastiest ones are the odd-order products, for example, third-order, fifth-order, and seventh-order intermodulation products. Here we see the expressions for the frequencies of the third-order, fifth-order, and seventh-order intermodulation products. Note, they always appear in pairs. Another interesting question is how many interfering intermodulation products can be expected. Assume we have P channels busy, then the number of possible intermodulation products is P times P minus 1. Some examples are found in the table. For P equal to 2, the case we have studied so far, 2 interfering intermodulation products are expected. In a GSM band, there may be about 170 channels, which gives rise to approximately 30,000 intermodulation products. Where will the interfering intermodulation products be situated? Assume our transmitters operate in a frequency band ranging from the lower frequency FL to the upper frequency FU. The third-order products will be situated symmetrically in 2 bands around the frequency band used by the transmitters. The bandwidth of the intermodulation products will both be equal to the width of the original frequency band. The fifth-order products will occupy twice the bandwidth of the original band symmetrically. And finally, the seventh-order intermodulation products will occupy 3 times the original bandwidth on both sides as shown in the figure. So, higher-order intermodulation products occupy larger bandwidth, but are commonly weaker. Looking in a table of the frequency allocations for some common services, the familiar GSM bands can be found. Let us take a closer look at some of the bands and what the structure of the possible intermodulation products looks like. For instance, take the extended GSM 900 band. The downlink, drawn in yellow, ranges from 925 to 960 MHz. The frequency bands of the intermodulation products are drawn in purple, blue, and pink. The uplink band is drawn in green. It can be seen that the intermodulation products of the 5th and 7th order overlap the uplink band completely. Further, also a large portion of the 3rd order products overlap the uplink. There is a potential risk of interference in our receivers due to the intermodulation products originating from the transmitters in the downlink. Looking at the GSM 710 band, the situation is the same, except we have other numbers. If we add the GSM 750 band to the picture, it looks like this. In this case, the interference situation is worse. The uplink of the GSM 750 band experiences interference not only from intermodulation products of the GSM 750 downlink, but also from the GSM 710 downlink. What is causing the nonlinear behavior? There are basically 2 mechanisms identified so far. The first one is that the material itself is nonlinear. For example, some magnetic materials may exhibit a nonlinear performance due to the fact that the current causes magnetic fields and that the magnetization curves are nonlinear for strong currents. In other cases, the nonlinearity of a material may be caused by polarization issues. The second mechanism is caused by surface effects in the interface between 2 materials. For example, Oxidization on the contact surface may contribute to MIM diode. MIM stands for metal insulator metal. This is a nonlinear quantum effect. MIM diodes suffer from poor mechanical stability, but they can operate at very high frequencies, about 10 terahertz. They have also been considered for solar energy conversion. The diagrams show current voltage characteristic curves for some MIM diodes. Nonlinearity may in some cases be useful. In old crystal sets, a nonlinearity was intentionally created pointing a needle on the crystal. In this way, the audio signal encoded in the radio frequency signal from a broadcasting station could be recovered. A typical amplitude-modulated radio signal consists of a carrier and sidebands containing the audio signal. The crystal realized the nonlinearity, for instance the current equals to the voltage V squared. The nonlinearity caused intermodulation products. One of them was the original audio signal encoded in the radio signal. Other products were direct current and high-frequency signals that were easily removed using filters. We have had wireless transmission for almost 150 years. Why is PIM a growing problem today? Well, the PIM problem has been known for a long time by people designing, for instance, cell phones, antennas, connectors, and space probes. Applications where strong radio signals are present in confined spaces. But during the past years, more and more users and services need to coexist in the radio spectrum, being an important asset. So, lower and lower noise and interference levels are required. Another factor aggravating the PIM problem is the practice of integrating the antenna, the electronics, and the cabinet of telecommunication devices. The more parts that are being exposed to strong electromagnetic fields close to the antenna, the stronger the currents and the greater the risk of PIM. Finally, how can PIM be measured and what are our goals in this area? There is a standard, IEC 62037, for measuring PIM. The test system basically mimics the situation in a base station or a cell phone. Two strong transmitters deliver signals to the device under test, the DUT. Intermodulation products generated in the DUT is reflected back to the receiver where the amplitude is measured. The DUT is commonly a connector, a coaxial cable, or a filter. There is no standard available today for testing, for instance, EMC gasket materials. For that reason, we are developing a fixture to be able to do such tests. The equipment used is a standard test system, a PIM master from Anritsu. This picture shows two sample screen dumps from the PIM master. Frequency is on the x-axis and PIM power in decibels on the y-axis. Our goals in the research collaboration between Nolato and Orebro University are to establish an efficient PIM test method for EMC gasket products and to improve our products to minimize PIM impact while maintaining the good screening properties. Thanks for watching.